Welcome everyone. Welcome to the seventh part in the series Analog Electronics. We have already covered tutorials on semiconductors, PN junction, rectifiers, transistor, transistor configuration, and operational amplifier. The link to those tutorials are provided in the description below. I would suggest that you first go through the tutorial on operational amplifier before proceeding to this particular tutorial. That tutorial will be very helpful in understanding the contents of this particular tutorial. The link to that tutorial on operational amplifier is provided in the I button on the right top corner. In today's tutorial, we are going to look into inverting amplifier, non-inverting amplifier, voltage follower, summing amplifier, and subtractor. In the next tutorial, we will be looking into integrator, differentiator, comparator, and zero crossing detector. The open loop gain of the op amp is very high, usually about 10 to the power of 5. So, if we provide an input of 1 millivolt, the output would be 100 volt. Now, the op amps are generally operated at voltages less than 20 volt. So, this voltage of 100 volt will drive the op amp into saturation. So, you can see that the op amp with open loop cannot even handle a voltage as low as 1 millivolt, and hence it is required that we bring this gain to a value where it can be used for different higher voltages as well. So the op amp is operated with a negative feedback. In case of a negative feedback, a part of the output is fed back through a feedback resistor in phase opposition to the input. With negative feedback, the voltage gain can be reduced and controlled so that the op amp can function as a linear amplifier. The gain in this case is called as closed loop gain as opposed to the open loop gain in the previous case. Let us look into the operational amplifier's characteristics in case of feedback and no feedback. On the left we are having characteristics without feedback, and on the right we will be having characteristics with the feedback. So the voltage gain is too high for an application as linear amplifier without the feedback, whereas the voltage gain can be set to a desired value in the linear range because of the feedback circuit. So with the feedback, you can operate the op amp in a linear range. The input impedance is relatively high without the feedback, whereas the input impedance can be adjusted to a desired value with the feedback. The output impedance is relatively low without the feedback. In case of with feedback condition, the output impedance can be reduced to a desired value. So the input impedance and output impedance without feedback are fixed, whereas with feedback you have the option to put it at a value wherever you like. The bandwidth without feedback for an operational amplifier is relatively low, whereas it is significantly wider with feedback. So the operational amplifier is generally operated with feedback. Now let us move on to the applications of the operational amplifier. In this tutorial we will be looking into 5 different applications, and all will be with the negative feedback. First is the inverting amplifier, in which the input V in is provided to the inverting terminal of the op amp. The inverting terminal is denoted by the minus sign, whereas the non-inverting terminal, which is grounded, is denoted by the plus sign. The input is fed through an input resistor Ri, and the input current is given as Ii. The output is given as Vout, and the feedback circuit is of a resistor Rf. The current through the feedback resistor is If. If we provide input voltage, as you can see on the left of your screen, the output is obtained as shown in the right of the screen. The output is amplified but is 180 degree out of phase with the input. and that is why this amplifier is called as the inverting amplifier. The inverting amplifier gives rise to a very interesting concept called the virtual ground. Now, we know that the op amp has very large input impedance, which means that negligible current can flow into the op amp at the inverting input. We will take this current to be 0. That is, there is no current flowing through the op amp. So if there is no current through the input impedance, then there will be no voltage drop at the inverting and non-inverting inputs. This means that the voltage at the inverting input will be equal to the potential at the non-inverting input. Now, the non-inverting input is at ground, that is 0 volt. So the input at inverting is also at 0 volt. This is called as the virtual ground. Let us look into the mathematical explanation of inverting amplifier. No current flows through the inverting input of the op amp, that is condition 1, and condition 2 is that the current flowing through the input resistor is same as the current that flows through the feedback resistor, that is IF equals to II. We can represent it as 0 minus V out by RF equals to V in minus 0 by RI, as there is no voltage at the summing point. So if we do further mathematics, we get this equation: V out by V in equals to minus RF by RI. This V out by V in is nothing but the voltage gain, which can be represented as AV. So AV equals to minus RF by RI. RF by RI is the magnitude of the gain, and minus sign represents inversion. So the output voltage is minus RF by RI V in. The output is amplified according to the ratio RF by RI and is inverted as represented by the negative sign. Let us move on to the next non-inverting amplifier. In this case, the feedback circuit is grounded, whereas the input is provided to the non-inverting terminal. So, going back to the previous case, the input impedance of the op amp is high, and hence no current will flow through the op amp. So the voltage at the inverting terminal will be same as the potential at the non-inverting terminal, which in this case is V in. So if we provide an input, you receive the output like that. The output is amplified and is in phase with the input, and hence it is called a non-inverting amplifier. Let's move on to the mathematics of the non-inverting amplifier. The negative feedback, as you can see, is provided through the resistors RF and RI. That is, the current through RI is equal to the current through RF. Again, writing the equation, we find this. Solving it, we get V out by V in equals to RF plus RI by RI. As we know that this is the voltage gain, AV, which is 1 plus RF by RI. So the output voltage is 1 plus RF by RI into the input voltage. The gain in case of a non-inverting amplifier is always greater than or equal to 1, and the output is always in phase with the input. One very interesting use of the non-inverting amplifier is the voltage follower. In case of a voltage follower, the entire feedback circuit has been removed and the output is directly fed to the input, the inverting input. The non-inverting input is used for providing the voltage. So in this case, the gain is 1. That is, the closed loop gain is 1. So if you provide an input, you will find an output which has the same magnitude and is in phase with the input. The input impedance is very large and the output impedance is very low. It is used as a buffer amplifier to be connected between high impedance sources and low impedance loads. Let us move on to another interesting use, the summing amplifier, or as it is famously known as the adder. In this case, we have used three voltages. You may use more, but you have to use at least two. So we have used three voltages, V1, V2 and V3, which are fed to the inverting terminal through resistors R1, R2 and R3. The corresponding currents are I1, I2 and I3. The feedback circuit has a resistor RF with the current IF. If we give input voltages like this, we will receive an output voltage which will be out of phase with the input and will be the sum of the inputs. Let us look into the mathematical expressions. Using the conditions for inverting amplifier and the Kirchhoff's current law, the feedback current is equal to the algebraic sum of the input currents. Writing the electrical equations, we get the output voltage to be minus of Rf by R1 V1 plus Rf by R2 V2 plus Rf by R3 V3, where Rf by R1, Rf by R2, Rf by R3 are the individual voltage gains for the inputs. We may do an approximation that all the input resistances are same, that is equal to R. Then the output voltage becomes little simpler to understand, minus Rf by R into V1 plus V2 plus V3, that is gain into the sum of the voltages. We can do another approximation in which Rf is equal to R, and therefore the output voltage is simply the inversion of the algebraic sum of the input voltages. Another interesting application can be when R equals to 3 times Rf. Here the output is the average of the input voltages. Let's move on to the last application in this particular tutorial, the subtractor. In subtractor, you will have two inputs, V1 and V2, which will be provided to the inverting and non-inverting terminal respectively. The input resistances in both the cases are to be same, and the feedback resistances are also to be same. This condition needs to be maintained. I1 and I2 are the current for the inverting part, I3 and I4 are the current for the non-inverting part. At the summing points, V and V dash are the voltages for inverting and non-inverting terminals. So we have two conditions. If V1 is greater than V2, then the output is inverted as the inverting terminal input is having a larger magnitude. The entire voltage is basically a subtraction of both the values, but it will follow the phase of the inverting terminal, that is, it will get inverted. Whereas if V1 is less than V2, that is the non-inverting terminal has a larger value, then the output follows the non-inverting rules, that is, it will not invert, and again it is a subtraction of both the values. Let us look into the mathematics. At the inverting input, I2 equals to I1. So we get this equation, V minus V out by R2 equals to V1 minus V by R1, which can be represented in this form, V into 1 by R2 plus 1 by R1 equals to V out by R2 plus V1 by R1. At the non-inverting terminal, I3 is equal to I4, and we receive the equation V dash 1 plus R2 plus 1 plus R1 equals to V2 by R1. Now, as the open loop gain of an op amp is very high and no current flows through it, so V and V dash are practically the same. That is, the right side of above two equations can be equated, and we get the output voltage to be V out equals to R2 by R1 into V2 minus V1. We can do a little bit of mathematics here, where if R2 equals to R1, then the V out can be simply represented as V2 minus V1. So these were the 5 applications of operational amplifier. In the next tutorial, we will be looking into integrator, differentiator, comparator, and zero crossing detector. Till then, stay healthy, stay safe. Thank you.